Okay, so here's the homework solutions for chapters 6 and 7. There's a lot here. I said it took a while, so hopefully you took a while also. So the conceptual questions, hopefully not too bad. As soon as someone's launched, their weight's going to be zero um, because they're in free fall, unless there's another force acting on them. But could be no normal force. Otherwise, again, they're not in free fall. For 13, if you're looking at a book being pushed into the table and look at the forces on that, the normal force in the book from the table is greater than the force of the hand on the book or mg in the book because those two forces act down and the normal force acts up. For problem 31, we've got an elevator and it's on the 50th floor, and your first thing is to determine whether the elevator is initially going up or down. Well, you know that an elevator is going to accelerate at the beginning of its trip and at the end of its trip, and the middle will be going at pretty constant speed. So that constant speed lets us figure out that the person's weight or the gravitational force on them is 750 newtons, meaning they're about 75 kilograms. That's part B. But since now we can go back and look and say that the initial part, the person's weight according to the scale, is less. That means that the elevator is accelerating downward. So if it starts in the 50th floor, it's going to end up heading lower. To find how far the elevator travels, this is actually pretty useful to find the accelerations. So I can go back and think about the acceleration in each of these cases from 0 to 2 seconds and 10 to 12 seconds. From 0 to 2 seconds, I know that the missing force is 150 newtons. So I can think about the fact that that would cause an acceleration downward of 2 meters per second squared. And in fact, the acceleration calculation here would be -2, or 2 down. So if you start from rest and are accelerating at 2 meters per second squared for 2 seconds, you end up traveling 4 meters. You also end up going 4 meters per second. So I'm using that constant speed in the middle part of the trip from 2 to 10 seconds, figure out how far the elevator travels then. And then there's some symmetry at the end of the problem. So if you travel 4 meters while accelerating up to 2 meters per second squared in 2 seconds, you would also travel 4 meters when slowing down. You could use a version of this formula that's different, which is VIT plus 1/2 AT squared, since you know your initial velocity. But since acceleration and your initial velocity are pointing opposite directions, they partially cancel out. You'd still end up with the same answer. So this is 40 meters. For problem 33, this was a good one. It was where something was in traction, and traction is basically where you don't want there to be any force up or down on the objects because you want the bones to heal properly, but there's a pull out. So you're basically using that to separate the bones so that then they can heal in the proper position. So to do that, we've got a bunch of pulleys. We've got tension in a rope here, which I'm going to assume is massless, a couple different angles. So the tension in the rope, I can look at this part. I know that if it's 6 kilograms, that's 58.8 newtons, and that's the force down, and so that's got to be the tension up. To pull straight out, which is what traction needs to do, we need to realize that the upward force, which is basically caused by the vertical component of this tension, would have to equal the downward force, which is the vertical component of this tension, plus the weight of the foot. So I'm going to say that tension times the sine of theta, so the vertical part of this, is equal to the tension times the sine of 15 degrees, which is the vertical part of this, plus the weight of the earth on the foot, 39.2 newtons. I'd already figured out the tension, so I plugged that in, and I end up getting that the angle that thing has to be at is 67.7 degrees from horizontal. So it's pretty vertical. It's a little different than the picture. The last part is figuring out the traction force, which is force pulling outward. There I'd simply add up the horizontal components of this tension and this tension. Problem 35 is a small calculusy problem. So if you take the second derivative of position versus time, you get an acceleration function. And you can then determine at 0 seconds and at 1 second what the acceleration is. And then if you use Newton's second law, F equals m times a, you can figure out what the net force is. So the M is 2 kilograms, the A at 0 seconds is -6, the A at 1 second is +6. So I get -12 newtons and 12 newtons. Here, 55 is sneaky because you needed to know the coefficient of friction of wood on wood, which is in your chapter. So for static friction, it's less than or equal to 0.5. So in this particular case, what I'm looking at is, what direction would the box accelerate, and if it does, what is the magnitude of acceleration? So I'm finding the upward force due to this push is 6 newtons. That's the vertical component of this force. The downward force is equal to the weight of this box, which is 9.8 newtons. Now, if I want to find friction, friction is the horizontal component of the normal force. So in other words, the normal force is a certain amount, which here would be 10.39 newtons. The frictional force could be up to half of that based on that coefficient. So up to 5.2 newtons of friction. That's the maximum you could have for static friction. So the box isn't going to move because the difference, that's fantastic, because the difference of these two forces is less than 5.2 newtons. So in this case, with how this person is, the gravity is acting and how the person is pushing, we need an extra force up. So that means that friction is acting upward. So I could even push a little bit harder upward and the box would still not move. So I think I give a pretty good explanation down here. Hey, there's my hand. For chapter 7, these 3 questions are pretty straightforward. So question about a tug of war, question about a toy with a magnet on it, and about a spring scale. So those ones, this one's basically due to the fact that the magnetic interaction with the cart is an internal force to this whole system. Tug of war is kind of interesting, especially when you start thinking about Newton's third law. You're like, hey, that seems a little weird that someone can win, but it's really the interaction of the team with the ground. That's why successful tug of war teams tend to be made of very heavy people. So they have a lot of normal force with the ground, and therefore they have a lot of frictional force with the ground. So problem number 9, you got a truck or a car pushing a truck. You got the different masses, and you have the net force that the engine's acting on the ground. So that's the net force forward on the system. So I can get the acceleration here. Part B is finding the force of the car on the truck. So then I'm isolating just the truck. If the truck is accelerating at this rate and the truck's mass is 2,000 kilograms, then I can find the force of the car on the truck. And that therefore must be also the force of the truck on the car. If you drew a free body diagram on the car, or the forces in the car, you'd see the truck is pushing 3,000 newtons backward to the right, and you'd see that the car is therefore still pushing 4,500 newtons forward to the left. That's why the car accelerates. Chapter 7 problems. They've got a cat hanging here and a dog hanging here. They're toys, I guess, and we're assuming that this tension is completely static. And your goal is to find T3 and angle 3. So to do this, I know that this angle, and I know the weight of the cat. So I've got to really start at the left end, figure things out, and work my way right. So the first thing is recognizing that the force of the cat down here will equal the vertical component of this tension. And since we know the angle, I can figure out the tension. T1 is 57.3 newtons. At this point also, I know that the leftward component of T1 would equal the rightward component of T2. So I can use trig to find the leftward component of T1, which is this, 53.9 newtons, and that equals T2. So I call this point X. Point Z, which I've got in green here, I know that the leftward component, or the leftward force of T2 would equal the rightward component of T3. So, and I also know that the downward component here would equal the vertical component of T3. So I have two separate equations. T2 is equal to T3 cos theta 3, and T3 sine theta 3, which is the upward component of T3, would equal the weight down. So because of that, I can rearrange to solve for T3 here, and T3 here, and I can put those together. So I can say this 39.2 over sine theta 3 and this 53.9 over cos theta 3 are equal to each other. If I end up cross multiplying, we get 39.2 over 53.9 equals sine theta over cos theta. Hey, that's tangent of theta. So we know the tangent of theta is 0.73, and I can get my unknown angle. Once I have that angle, I can plug it into any of the equations where I have T3 already. So I just used this one up here, and I solve for that. So those two boxes are my final answers. This is actually kind of interesting for 27. We end up with a starship having a tractor beam on a shuttlecraft. So they're using basically a fake science fiction analogy, but they're also using it to show that, wow, that tractor beam is going to affect both ships. So the way I thought about it was, if I know the force of the tractor beam, I could figure out the acceleration on the shuttle and the acceleration of the starship. Since they're going to approach each other, because that's what a tractor beam does, it brings things in, then the combined acceleration of that system is that they're approaching each other at 2.02 meters per second squared. So I know the distance between them, I know the net acceleration, I can figure out it's going to take about 99.5 seconds for that to happen. Now, if for some reason the starship wasn't accelerating at all, it would take 100 seconds. So your answer wouldn't be very far off here compared to here. But what that does tell us is, now if I know the acceleration of just the starship, the time it's accelerating, I can get 99 meters is how far the starship moves. So it's basically about 100 to 1 ratio. Because the starship is 100 times its mass, it'll only move about a 100th as far as the shuttle. P28. I'm trying to remember what this is. Oh yeah, this is some ball hitting the forehead or hitting the cheekbone. So need to figure out the acceleration of the ball. Is it stopping? And basically to do that, you need to know what 1.5 ms is 1.5 milliseconds. So you get an acceleration of 20,000 meters per second squared. So if you know the mass of the ball, you can figure out the force necessary to stop it in that amount of time. But the problem is the cheekbone cannot withstand that. The forehead can. So don't get hit in the cheekbone. Problem 35 is a very good problem. I'm going to probably go over this in class. Drawing the picture really helps. The thing that's sneaky is there's 3 frictional interactions. So you have this force that's an external force pulling to the right. That'll make the 2 kilogram block go to the right. Therefore, friction is acting to the left on the 2 kilogram block when it's interacting with this surface. That's slowing the 2 kilogram block down from the rate at which it would otherwise accelerate. We would find that out by the total normal force, which is 3 kilograms times g, multiply the coefficient of friction, which is given as 0.3. There's also friction here between the top 2 blocks. Now, most people, my guess is they'd figure out that there's a friction on the 1 kilogram block caused by the 2 kilogram block. Okay, so that's mu mg. But the thing is because that's an interaction, there's also an interaction from the 1 kilogram block on the 2 kilogram block. So if you look at this, and I put 2 and 3 here, then the 1 kilogram block would be going to the left. Friction from the 2 kilogram block is acting on it to the right, thus slowing it down. Newton's third law with interactive forces says that if the force from 2 on 1 is acting to the right, the force from 1 on 2 is equal in magnitude and acting to the left. So that says that the friction with this 1 kilogram block is also acting to the left on the 2 kilogram block. So that is a sneaky thing. This is actually a really good thinking problem. I can only imagine it would get better if this pulley actually had some mass. So that's how I get my net acceleration. Talk a little bit about it down here. 46 is the last problem. It's called a bosun's chair, where this person is pulling themselves up, and it helps to really draw this free body diagram. So the rope is attached to the chair, but the person's holding the other end of the rope. So essentially, to accelerate him or herself upward, the force of the rope has to only be a little over half as much as the gravitational force down. Why? Because the rope is contacting at 2 points. So that's why you have a mechanical advantage with pulleys. You have multiple strings that are essentially doing the work. So in this particular case, I've got the force of the rope on the chair. I call the force of the rope on the painter. That's also tension. Don't know why I didn't put an end parentheses there. And the gravitational force down. Those two upward minus that downward would cause an acceleration of 0.2 meters per second squared upward. So that's a net force of 16 newtons. So that 16 newtons is over here. 2 tension up minus gravitational force down. About 400 newtons of tension in the rope. So I'm hoping that these help. Like I said, these are really good questions, and I wanted you to see some things with multiple steps like that before we have our next test.